This is joint work with Valeria Boncompagni and Kristina Vuskovic, and we're all from the University of Leeds in the UK. So let me just start with a few basic definitions. First of all, a graph G contains a graph H if H is isomorphic to an induced subgraph of G. And G is H-free if it does not contain H. If we have a graph G and a family of graphs F, then G is F-free if G is H-free for every graph H in the family F. A class of graphs is hereditary if it is closed under induced subgraphs, which of course means that whenever you have a graph in the class, all induced subgraphs and their isomorphic copies also belong to the class. Of course, if you have any family of graphs, the class of F-free graphs is hereditary, and that's just obvious, right? Because if a graph is F-free, then of course so are all its induced subgraphs. Now we are interested in several classes of graphs that are defined by forbidding certain trumper configurations. So those are thetas, pyramids, prisms, and wheels. If you don't know what those are, don't worry, I'll tell you in just a minute. But before that, I just wanted to say that these kinds of configurations have appeared in the context of various hereditary graph classes, perhaps most famously perfect graphs, but also others. Sometimes they appear as forbidden induced subgraphs. Sometimes they appear as induced subgraphs around which you can just decompose the graph, and that's just for the purposes of proving decomposition theorems. So there are two types of trumper configurations. There are three-path configurations, and there are wheels. Let's start with the first. So three-path configurations, well, that's thetas, pyramids, and prisms. And I have drawn them in the picture. I should probably say this full line represents an edge. A dotted line, that's a path of length at least one, meaning it has at least one edge. Why are they called three-path configurations? Well, because in each case you can cover the vertex set with three paths that are internally disjoint. So I have colored these paths, red, blue, and green. Also, notice that whenever you take, well, any one of these three types of 3PC, and you take any two of these three paths, well, they together induce a whole. A whole is just an induced cycle of length at least 4. So we have three paths. You have three ways of choosing two of them, so you get three distinct wholes. And then there's this other type of trumper configuration, namely a wheel. So a wheel, that's a graph that consists of a whole plus an additional vertex that has at least 3 neighbors in the whole. And I have drawn, well, some small wheels in the picture. Okay, so as I already said, a trumper configuration is any 3PC, three-path configuration, or a wheel. So a couple of remarks. Every trumper configuration contains a whole. I explained this for 3PCs. And as for wheels, well, that's just a part of the definition of a wheel. And that, of course, implies that chordal graphs do not contain any trumper configuration. So a chordal graph, by definition, is a graph that does not have any holes, does not contain any holes. Every trumper configuration contains a hole, hence chordal graphs contain no trumper configurations. Now, chordal graphs are very famous in the well-studied class of graphs. There's notably this nice decomposition theorem for them, which says that if you have a chordal graph, then it's either a complete graph or it admits a clique cutset. So a clique cutset is what you see in the picture. So I represent cliques by these shaded circles. So a clique cutset, that's just a clique whose deletion yields a disconnected graph. So in this case, A is separated from B if you delete C. C may possibly be empty, so if you have a graph that's disconnected to begin with, then the empty set counts as a clique cutset. Now, let's generalize chordal graphs. Let's say that a graph G is universally assignable if whichever way you assign parities to the holes of the graph, you can find some assignment of 0 or 1 weights for the edges of the graph, such that for each hole, its weight, meaning the sum of weights of its edges, has the parity that you prescribe to it, and furthermore, every triangle has odd weight. Clearly, chordal graphs are universally assignable. Chordal graphs have no holes, so you don't have to worry about prescribing parities to the holes. You just need every triangle to have odd weight, and you can accomplish that by assigning weight 1 to each edge. Now, what's more interesting is this theorem, which says that a graph is universally assignable if and only if it does not contain any trumper configurations. And furthermore, there's this nice decomposition theorem that's just slightly more general than the one for chordal graphs, and it says that if you have a universally assignable graph, then that graph is either a complete graph, or it's a whole, or it admits a clique cutset. Now, what do we want to do? Well, what we wanted to do was to generalize universally assignable graphs, and the way that we're going to generalize them is by allowing certain trumper configurations to appear as induced subgraphs, and in particular, certain types of wheels. So to that end, I have, 3 types of wheels. The first type are the so-called universal wheels. So that's when you have a hole plus a vertex that's complete to the hole, and that's what you have in the picture. The second type are twin wheels, so that's a hole plus an additional vertex that's adjacent to 3 consecutive vertices of the hole and nothing else, so it's a twin wheel. And the proper wheel, well, is every other kind of wheel, so it's a wheel that's neither a universal wheel nor a twin wheel. And the class that we are interested in is the class GUT. This is the class of all 3PC proper wheel free graphs. So why is it called GUT? Well, U stands for universal wheel, T for twin wheel. We think of this as the universal wheel, twin wheel only class. Why? Well, because graphs in this class may contain universal wheels, may contain twin wheels, and may not contain any other trumper configuration. We're also interested in 3 proper subclasses of this class. So first we have this class GU. This is the universal wheel only class. So this is the class of all 3PC proper wheel, twin wheel free graphs. Graphs in this class may have universal wheels, but no other trumper configurations. And then similarly, we have this class GT, the twin wheel only class. This is the class of all 3PC proper wheel, universal wheel free graphs. Graphs in this class may have twin wheels, but they may not contain any other trumper configurations. And then finally, there's this 4th class, which is the class, GUT cap-free. So this is the class of all 3PC proper wheel cap-free graphs. A cap is what you see in the picture. So that's a graph that consists of a hole of whichever length you like, plus an additional vertex that's adjacent to 2 consecutive vertices of the hole and to nothing else. Clearly, caps are not trumper configurations, so this 4th class differs from the previous 3 in the sense that, well, for the previous 3 classes, we were only excluding trumper configurations, and for this 4th class, we also exclude this something else, this cap. And here's kind of a schematic representation of the relationship between the classes that have been mentioned so far. Arrows just indicate inclusion. Chordal graphs are the smallest. They're included in everything else. And this class GUT, the universal wheel, twin wheel only class, well, it contains everything else as a subclass. And the other inclusions are just indicated by arrows. Okay, so we have 3 types of results. We have structural results, we have chi-boundedness results, and we have algorithmic results. And I'm going to start with structural results. For each of our 4 classes, we obtain the decomposition theorem, and all the decomposition theorems are of the same form. They say something like this. So every graph in our class is either basic, that is, belongs to some basic class B, or it admits a clique cutset. So this is similar to what we had for universally assignable graphs and also for chordal graphs, except the basic class is more complicated. And furthermore, obviously, each class has its own basic class. So I haven't told you what the basic classes are. So for these theorems to make sense, I need to do that. So I'll be defining the basic classes in terms of anti-components. So what's an anti-component? Well, an anti-component of a graph G is an induced subgraph of G, let's say H, such that the complement of H is a component of the complement of G. So in that picture on the left, I have circled the anti-components. If you take the complement, those anti-components turn into components. Clearly, anti-components are complete to each other. That is to say, whenever you take any 2 of them, well, they're all possible edges between them in the graph. Furthermore, anti-components are divided into trivial and non-trivial. Trivial means it has just 1 vertex. Non-trivial means at least 2 vertices. So in that picture, those 2 circles on the bottom right? So those are the trivial anti-components. And the 3 circles on top, that would be the non-trivial anti-components. Clearly, if you take all the trivial anti-components together, well, they're complete to each other, so they form a clique, and they're also, each of them is complete to everything else. So trivial anti-components together form a clique that's complete to the rest of the graph. So the next thing I need is 3 types of graphs, the first 2 of which are shown on this slide. So what's on this slide is quite simple. We have hyperholes and hyper-antiholes. A hyperhole is what you get by starting with a hole, and then you blow up each vertex to a clique. The cliques can be of whichever size you like. They don't have to be all of the same size, just any clique you like. And then for hyper-antiholes, well, it's similar. You start with an antihole. An antihole is just a complement of a hole. And then you just blow up each vertex to a clique. So those are hyperholes and hyper-antiholes.
So the edges between cliques are complete?
Yes. So when you have an edge, that means they're complete to each other. And when you don't have any kind of edge between the circles, that means that they're complete. Yeah. And then we have something a bit more complicated. This is called a ring. So I wrote the definition on top, but I think it's probably easier to look at the picture than to read the definition. So a ring it's a kind of graph where you can partition the vertex set into k cliques. K is at least 4. And you can arrange those cliques in kind of this circular fashion so that for each of the cliques, vertices in that clique may have neighbors in the neighboring cliques, neighboring in the circular order, right? And they may not have neighbors in any other clique. So furthermore, if you zoom in on any one of these cliques, let's say xi, and its 2 neighboring cliques, xi minus 1 and xi plus 1. Well, in this middle clique, xi, you can order the vertices in such a way that the closed neighborhoods are nested. So the one on bottom has the biggest closed neighborhood and the one on top the smallest, right? And it's all nested. And furthermore, the one with the biggest neighborhood, the one on the bottom, actually has to be complete to both cliques. So the one on the left and the one on the right. So that's a ring. And notice that this generalizes a hyperhole because there is nothing stopping these cliques from being complete to each other where I have these wavy edges. So they may be complete to each other, and if they all are complete to each other, then that's just a hyperhole. So this is just a generalization of a hyperhole. Okay, so now I can start defining my basic classes. So let's start with the basic class for the GUT, for the class GUT. So this is the class of universal twin wheel only graphs. So this class BUT is the class of all graphs that satisfy one of the following 3 properties. So the first possibility is that G has exactly 1 non-trivial anti-component, and this anti-component is a ring of length at least 5. So what's the length? That's just the number of cliques, right, in this circular ordering. So what does this mean? So you may have possibly trivial anti-components, so that means that the graph is either precisely a ring of length at least 5, or you can obtain it by taking a ring of length at least 5 plus a complete graph and then making them complete to each other. So that's the first possibility. The second possibility is that the graph is long hole K23, C6 complement free. A long hole is a hole of length at least 5. Notice that K23 is a theta, which is why you have to exclude it. And then C6 complement, that's a prism. That's why you have to exclude it. The third possibility is that the graph has stability number 2. And furthermore, every anti-component is either a 5 hyperhole or a C5, C6 complement free graph. And then this theorem on the bottom, you've already seen it, but now it makes sense because you know what the basic class is. So it says that every graph in GUT either belongs to this basic class that I just defined or it admits a clique cutset. The second class, BU, this is the basic class for the universal wheel free class. For the universal wheel only class. So BU, that's the class of all graphs that satisfy one of the following. Either, so the first outcome is that G has exactly 1 non-trivial anti-component, and it is a long hole, meaning either the graph is a long hole, or it's a long hole plus a complete graph that are complete to each other. And then the second possibility is that all non-trivial anti-components are isomorphic to K2 complement. So the edgeless graph on 2 vertices. And the theorem, again, is that every graph in GU either belongs to BU or admits a clique cutset. The third one, okay, BT, so this is for the twin wheel only class. So the basic class BT is the class of all complete graphs, rings, and 7 hyper anti-holes. And the theorem says that every graph in GT, so this is a twin wheel only class, either belongs to this basic class BT or admits a Clique cutset. And then the fourth class, I think I'm going to skip just to save some time because I want to talk about, well, I want to move on to chi-boundedness. So first of all, what's chi-boundedness? Let's say we have a hereditary class G. It's chi-bounded if there exists some function f, which we call a chi-bounding function for G, such that every graph in the class, every graph G satisfies chi of G, the chromatic number of G, is at most f of the Clique number of G. The Clique number, of course, is the size of the largest clique. It's denoted by omega. Now, it's known that the class of theta-free graphs is chi-bounded, which immediately implies that our four classes are chi-bounded because, by definition, they're all theta-free. Unfortunately, the chi-bounding function that's obtained from this theorem in the middle is something enormous. It's super exponential, so that's not very nice, which is why we wanted to get better bounds. So we got these polynomial bounds for each of our four classes. The one on top, so for the biggest class of GUT, is a fourth degree polynomial function, and the other three are linear. For two of those smaller classes, we know we have examples showing that's optimal. For one of them, we don't know. The one for the class on the top, so GUT, we know for a fact that this is not optimal. So the bounds for these smaller three classes, they follow pretty easily from the decomposition theorems that we obtained. The bound for the biggest class, GUT, does not follow from the decomposition theorem that I showed you. So for that class, what we had to do was we had to prove a different decomposition theorem, which treats this last class, the GUT cap-free, as the basic class. So it said something like this. Every graph in GUT either belongs to GUT cap-free, so that's the basic class now, or it admits a small cutset. Small cutset meaning, well, the size of the cutset is bounded by a function of the Clique number of the graph. And then we have that this basic class GUT cap-free is chi-bounded. That's, well, we have that bound from the table. And then we bridge the gap between those two facts by a certain theorem that says that graphs of large chromatic number contain highly connected induced subgraphs of large chromatic number. That can easily be translated into a theorem about hereditary classes and chi-boundedness. And then you put all those things together, you do a little bit of algebra, and you get the bound on top. Okay, and then finally we have these algorithmic results. So we have four algorithmic problems: recognition, maximum weight stable set problem, maximum weight clique problem, and the optimal coloring problem. Our results are summarized in the table. Only one of them, as far as we know, was known before, so that's the maximum weight clique problem for the class GU, so that's due to the four people in the footnote. Everything else, as far as we're aware, is new. These results rely on, first of all, our structural results. Second of all, algorithms for Clique cutsets that are due to Tarjan. And then the coloring algorithm for hyperholes, which is not terribly difficult, but surprisingly difficult given the complexity of the simplicity, I should say, of the class. And finally, algorithms for handling chordal graphs due to, well, a bunch of authors. And I'd like to finish with just an open problem. So I'd like to draw your attention to the fact that we do not know whether the class GT is polynomially colorable. So we don't know that. Why don't we know that? Well, because we don't know whether rings are polynomially colorable. This is the slide that you saw before, just a definition of a ring. So the question is, can rings be colored in polynomial time? For even rings, yes, that's very simple. Even meaning there's an even number of those cliques, k is even. But for odd rings, we don't know. If the answer is yes, well then we get that graphs in GT are also polynomially colorable. If not, well, if this is NP hard, that would be extremely interesting because that would imply that even whole free graphs are NP hard. So we don't know. Polynomial NP hard, we don't know. And that's all, so thank you.
Are there any questions for Irena?
Do your results also have any applications for balanced matrices?
So we haven't done anything with balanced matrices here, no.
Other questions?
Could you briefly describe what is the highly connected subgraphs and
Yes, well, okay, so you fix a constant C, fix a constant k, let's say they're positive integers, and then you have some function of those two It's something like maximum of c plus 2k minus 2 comma 2k squared. I think that was the function. So if you have a graph that has chromatic number bigger than that, then you can find an induced subgraph that is, well, k connected and has chromatic number bigger than c. So there's this drop in the chromatic number, but not by that much. And also I should say that that theorem was, well, we were not the first to prove it, we have the best bound. There are at least 3 papers with that same theorem, but our bound is the best.
Are there any other questions? If not, we'll move on to our next speaker.